Hello and welcome back, everyone. Moving on to chapter 4. This is a pretty exciting chapter. It's not usually included in multivariable calculus texts, so if you've taken the course before, you've studied some other texts, prepare for something new. But it's a pretty good chapter if we really are going to try to set ourselves up to handle the generalized Stokes theorem. So everything in the generalized Stokes theorem relies on this idea of a differential form. We're going to spend our chapter learning exactly what these are. So we're going to start out with defining them. That's really what the entire first section is about. And I want to get you all to pay attention to these dx's that have shown up in derivatives and integrals so far. Right? We've got the dx derivative, we've got the dx and the integral. These are the same object. And in the past, you probably referred to them as the differential of x. It is what we call them. But no one really has a good way of defining what this mathematical object is yet. I mean, today we're going to figure out exactly what it is, or at least the way differential geometers interpret this object dx. But you may have heard in some calculus course that dx can be thought of. This is really an intuition, so I've got it in quotation marks. The smallest possible positive quantity, right? It's called an infinitesimal. Infinitely small, yet positive number. Those numbers don't exist, at least in the sense of real numbers, in something called standard analysis, so, the standard way that we mathematicians like to interact with one another, along with the real numbers. Obviously, this smallest positive real number doesn't really exist. Now, that doesn't mean it's not useful to think about it intuitively as this smallest possible positive quantity. And indeed, we are going to rely intuitively on infinitesimals today. But the important thing is that nobody requires that all mathematical objects are numbers. And that's what we can get away with. We get away with the fact that even though we think about it as an infinitely small number, that's not what it actually is. It's something else. And the thing that is something else we'll get to eventually. But before we get there, I'm just going to introduce differential forms. In other words, we'll get to figure out ways of thinking about dx, dy, and dz, and in fact, higher dimensional versions of these. Because if dx is the smallest possible positive quantity, in other words, something in maybe the real numbers, what would be the equivalent in maybe R2, the two-dimensional real numbers, or the three-dimensional real numbers? Do we still have smallest possible positive R2 elements, whatever that might mean? And certainly we do. We're going to start with the differential K form. Now, this is going to seem really obtuse. It's going to come out of nowhere. It's not going to make any sense what these things are for a little while. We'll basically have to finish the chapter before you get a good idea of exactly what these things are. We're going to start with its definition, because the definition is not actually that hard to work with as long as you're okay with the extremely ugly notation of all these terms that I have here. So what is a differential form? And in fact, a differential K form. We care about that number K quite a bit. And K is going to correspond to the K that we see right here. So a K form is going to be a multidimensional function. We've been working with those the whole semester, so it shouldn't feel too bad. But the domain and the codomain are kind of fancy here. So the domain is fine. Domain is same as always. The codomain, we may need to figure out what's going on here. The codomain is a vector space. A very specific vector space. And this kind of helps out why we just covered vector fields. And so actually all of these differential forms are going to be vector fields because we interpret their outputs as vectors. This vector space happens to have n choose k dimensions inside of it. You'll notice that the vector space notation includes a k here and includes an n here. So somehow the dimension should depend on n and k. And it turns out it depends on the dimension n and k with the binomial coefficient. And if you've forgotten what that is defined as, it's n factorial divided by k factorial times n minus k factorial. And this counts the number of ways, possible ways, to choose k objects from a collection of n total objects. Now that just happens to be the dimension of the vector space, and I'll kind of describe why, as well as there is a single exercise in some of the assignments about trying to figure out why that's the dimension. But in many ways, you can just think this is the total number of distinct coefficients each output has. Right? That's how you can think about the dimension of a vector space, the total number of distinct coefficients ascribed to that vector space. And in some ways, why is it n choose k? Well, we have n dimensions to work with, which means that our functions will be f of x1, x2, x3, xn, right? It terminates at xn. So there's n possible choices for variables in this space. And because we're calling our objects k-forms, we're going to require that each direction, so these are the directions, these represent, I'm going to put them in quotes here, directions, because don't try to visualize what this means as a direction. It doesn't make sense necessarily. These represent directions in a vector space. And how many possible directions do we have? Well, we're going to form the directions symbolically, purely symbolically. We are forming the directions by including k total terms of the form dx with a certain, I'm using a superscript here, but the superscript corresponds exactly to the subscript in my variables. So dx with one of the superscripts, another dx with another possible superscript. That could be any of these subscripts from the earlier variables. And I'm going to keep placing these next to each other, surrounded by these things called wedges. That's our mathematical name for these. These are called wedges. It's just the notation people have decided on for differential forms. So we have wedges that are separating each of dx, and then I'm putting a superscript, which corresponds to the natural subscript that I have on different variables. I'm going to take k, total of those, and these superscripts are going to be distinct entries from 1 to n, right? So it's, in some ways, how many ways can I choose 1, 2, up to k elements out of this set 1 through n? That's why we're getting n choose k here. And we write them in a strictly increasing order. And so each one just has a different quote unquote direction associated to it. I'm just going to show you really quick. Suppose we're in 3 dimensions. So my variables are x, y, and z. Then how many different, let's say how many different 2 forms can I have? The only possible 2 forms can be, like these directions for 2 forms, can be dx wedge dy, dy wedge dz, dx wedge dz, right? So all I'm saying is if I want a 2 form, there's going to be 2 entries in each of these directions, and separated by a single wedge, and I'm taking distinct variables from my input. So I have 3 choices of variables. I'm going to take distinct ones, and then I'm going to write them in strictly increasing order, increasing in the sense of left to right in their original orientation as my inputs to the function. And so there's going to be 3 possible directions for 2 forms in 3 dimensions to exist within. I know that doesn't mean much for now. It's not supposed to mean much for now. This is just something we're going to construct, and then we're going to understand all of its properties later. So I do want to start with, it's going to turn out that a couple of these we've actually kind of seen before. So I'm just going to start out with the 0 forms. And if it's not quite clear yet, that's going to be n choose 0. N choose 0 is always 1 because there's only one way to choose 0 elements out of a bag of n total elements. So this will be the space of 0 forms is going to be a 1-dimensional vector space. And the possible directions to move in this space are going to be, well, none of these. I'm not going to include any terms in my directions. So in some sense, the 0 forms, I'm calling them scalar fields here. You can think about them as a 1-dimensional vector space of coefficients alone. Right, so they don't have a dx or a dy associated with them. It's just coefficients alone is my 1-dimensional vector space. We think of coefficient spaces all the time. I mean, your 1-dimensional calculus, x squared minus 2x plus 2, you did not write a dx as the direction in which this is existing against, right? You could have put that there, but you didn't. The fact that it's non-existent means that that is a 0 form. Okay, so 0 forms are basically the regular functions we all know and love, in the sense that they're technically scalar fields, though, because we decided that it's a 1-dimensional vector space on the output. So they can only have, they have n possible input dimensions, but they only have a single output dimension. Now, what do those look like? Or some good examples of those? We have this scalar field that you've been working with the entire semester. Right? Every sort of like surface, right, function from multiple variables. The one variable that you've been working with the whole semester is going to be one of these 0 forms. Here's another 0 form, function of 2 variables, 2 outputs. Here's another 0 form, function of 1 variable, 1 output. So regular functions you've been working with, as long as they have a single output, are considered 0 forms. I now claim that you've actually had experience with differential 1 forms as well. So we go back to the definition of differential forms. Right, if I replace that k with a 1, I'll replace k with a 1. I'm going to say n choose 1 here. Well, n choose 1 always happens to be n. So if I put a 1 here, this is now an n-dimensional vector space. And we know n-dimensional vector spaces are isomorphic, at least, to Rn, or in other words, we're looking at functions from Rn to Rn. In other words, we're looking at exactly the vector fields the last video was on. So the 0 forms are the scalar fields, the 1 forms are the classic vector fields that you were just working with. So I've got some examples of vector fields down here. So that means I have 3 inputs. If I have 3 inputs, I also need 3 outputs. And then we ascribe some meaning to each of the outputs, okay? So normally, when we saw vector fields in the last video, we were just kind of thinking about this object by itself, mapping real numbers to real numbers. As 1 forms, we ascribe new meaning to the outputs of a vector field. Okay, instead of just thinking them as a vector, Euclidean vector embedded in space, we're now thinking about the first entry output of my vector field as the coefficient for this object dx. Whatever dx happens to be, we'll eventually discover what dx is later. Think about the first entry in the output vector. A vector field is the coefficient of dx. Second entry likewise would be the coefficient of dy, and the third entry is the coefficient of dz. Whatever that means, right? We're not going to ascribe some sort of visual intuitionistic meaning to these differentials yet. We're just going to say, hey, where I used to think about a vector field as having a first entry, a second entry, and a third entry, I'm now going to think about that vector field as having a coefficient on dx, a coefficient on dy, and a coefficient on dz. Same information is contained in both of them, but the second one we will eventually ascribe a different meaning to, a different sort of vector meaning to it. Same, we can have a vector field from R2 to R2, here defined by g of xy is negative sine x sine y times sine y, and negative sine x sine y times cosine y. And just like with our 3-dimensional vector field above, we're no longer going to interpret that as just an x component and this is a y component, but rather we're ascribing the first the meaning of the coefficient of the object dx, and the second the coefficient of the object dy, whatever those objects may happen to be. So let me just rewrite it as coefficients of dx and dy. That's going to be another 1 form. And in fact, you can think about functions from 1 dimension to 1 dimension, even though before we had thought about those functions from 1 dimension to 1 dimension as this was like a scalar field or a 0 form. You can also think about that function as a 1 form, as long as you ascribe this output, right? You really do want to think about this output. Since we have the dx here, you want to think about the output as the coefficient of this object dx. So normally you just think about the output without any coefficients, but in the language of differential forms, we do want to ascribe it to have the coefficient dx. Now, on top of just experiencing vector fields or multidimensional functions, I have the following remark, which says you really, really have already encountered 1 forms. So I'm going to ask you to now compare the specific cases provided in the 2 previous examples. Is there any relationship between f and bold f, g and bold g, h and my second h? Let's look again. Here f is, right, an unbolded f, x squared y cubed z to the 4th. And the one that I've shown you, now I chose this out of nowhere. No, I chose this problem exactly to be, this is exactly partial x of the earlier f. And then this entry is exactly partial y of the earlier f. And then this third entry is exactly partial z of the earlier f. In other words, you can think about this, well, as ascribed as a vector, this is the gradient vector. Right, that's the gradient vector of my earlier scalar field. Or perhaps when I'm ascribing it some meaning with differentials, you should really interpret this as the total differential of the earlier f. So you've all actually already seen that. I mean, it's going to be the same for g and h. I mean, just so you can tell really quick, h, if I take a derivative of h, I'm getting 2x minus 2, right? So I'm getting 2x minus 2 here for h, and of course that's the derivative as well. So it turns out 1 forms are derivatives. They're kind of the total derivative of a scalar field, the 0 form. So you've already encountered 0 forms all the time. You've actually already encountered 1 forms all the time. We just kind of have this different location where we're giving each entry in the forms or assigning it to be the coefficient of differentials. That's what makes differentials forms special. But it does get a little trickier when we step up to 2 forms. So let's go back to the definition of differential forms and see if we can understand what's going to happen when I replace k with 2. So if I replace k with 2 up here, I'm going to have n choose 2 as the dimension of my vector space. Now that number is going to vary. It's going to vary depending on the size of n, so I won't really write down a closed form formula, even though one does exist for that number. It's not just equal to n like it was in the last case. These things grow as n grows, or they grow quadratically actually as n grows. So you're going to have more and more possible combinations of these directions as n grows. But let's jump back to the case of 3 dimensions. We saw each of dx, wedge dy, dy, wedge dz, and dx, wedge dz as really the only 3 possible kind of directions, these possible basis elements for the 3-dimensional case of 2 forms. So let's go back down to this example, and you'll see in the example, the first one I start with is a function of 3 inputs and 3 outputs. Now why did I choose 3 outputs? Well, we just saw that dx, wedge dy, dy, wedge dz, and dz, wedge dx were the only 3 directions you could possibly walk in the sense of this particular differential form space, the 2 forms, subset of 3 dimensions. So they're a 3-dimensional space, which means I just need a 3-dimensional vector to represent these forms. And so it turns out that the vector fields you were interacting with in the last video also work to represent differential 2 forms, but we're going to ascribe a different meaning to each entry in the vector now. So now what happens is that our first entry of our vector field is ascribed to the direction, it's the coefficient of the direction, and I've just chosen this as long as you're clear about the directions that you're assigning each entry. Obviously, there's no natural ordering to like x, y, and z when you put 2 of them next to each other. So I've just chosen that the first entry in my vector should be attached to the 2 form dy, wedge, dz. And so I'm going to use it as the coefficient of dy, wedge, dz. The second entry in my output I'm going to say is the coefficient of dz, wedge, dx. So I just use it as the coefficient of dz, wedge, dx. And the third I'm using as the coefficient of dx, wedge, dy. So there I've used the third as the coefficient of dx, wedge, dy. Now I again want to let you know that this does not really have meaning yet. It's going to feel like that was an arbitrary choice I made because I haven't ascribed any meaning to anything. This will all make sense eventually when we eventually encounter what do the meaning these objects have. We don't just take willy-nilly any vector field that already exists and start ascribing it directions in different form spaces. The form spaces will arise naturally, and then we'll be able to develop the correct vector fields that describe each of the form's directions. I do have another example of a case from R2 to R. There's only one possible, right? Only one possible 2 form from, starting in 2 dimensions when I have g of x and y. How many possible ways can I wedge x and y together? There's only one if I have to keep my order specific, so I only have a single output to this function, and yet if I ascribe it the direction dx, wedge, dy, I just consider it the coefficient of that symbolic term dx, wedge, dy. Now it really turns out that there isn't going to be 2 forms from one input dimension, because if I try, right, if even I attempt to try dx, wedge, dx would be my only choice, but the definition of my form said that the entries in these dx's or dy's or dz's, they have to be distinct, right? Distinct entries is required. And so it turns out there's only one possible, up to interpretation what you mean by one possible, there's only one possible 2 form on 1-dimensional domains, which is just a 0. Now I'm going to describe what is going on, especially in the case of dx. We now know, we've learned that dx can be interpreted as a 1 form, right? There's no wedges there, and it is existent. So the fact that it exists means it's not a 0 form, and the fact that there are no wedges means that it's not a 2 form or higher. So we can interpret dx as a 1 form. And how do we interpret 1 forms? Well, what's the coefficient? Coefficient on dx is exactly 1. There's a coefficient of 1 on dx. In other words, what is the 1 form that dx is assigned to? It's really this vector field, f of x, y, z, if I'm assuming 3 dimensions. It's the vector field 1, 0, 0. In other words, I'm ascribing the vector component 1 in the x direction and 0s in the y and the z direction. But of course, this is going to change depending on the size of my ambient space. If I have g of x, y, z, and w, it's still just, dx is still just the coefficient of 1 in the x direction and 0s everywhere else. Right? I can think of a function of 2 variables, x and y, it's a 1, 0, or even a function of 1 variable, let's say w of x is equal to just 1. Okay, so these are really all versions of dx. They're all vector fields where the x component of the vector field is constantly 1. That's how we should think about the object dx. And so that's what I've written down here. Right? We've got these vectors 1, 1, 0, 1, 0, 0, 1, 0, 0, considered as vector field, constant vector fields. But that is what the object dx is. It's all of those vectors. Now that's going to not make a lot of sense until I give you the following image. We actually have two spaces. There's this very fancy word. We're not going to worry too much about what it actually means mathematically. A fancy word called cotangent space. And that word cotangent space is the space that we define to have these vectors embedded within. These are elements of I'm just going to call it an irregular space. Irregular space, not regular three-dimensional space we exist in, we move around in. It's a brand new space, brand new vector space, give it some abstract notion. They're elements of an irregular space, and we give that space the name cotangent space. Obviously, you can probably see that word. It's not cotangent like the reciprocal of tangent, the trigonometric function. It's cotangent like the word tangent, like there's a space that is tangent to functions. These are the spaces of derivatives. Cotangent just means, you know how you took a gradient vector and that was a vector, but the derivative matrix was a row matrix. If you transpose the column vector of the gradient, you get a row vector. Co often means transpose. So it's the transpose of the gradient space is what it's trying to say. Anyway, we have that like irregular space called the cotangent space, and that is the space in which we ascribe a true vector representation to dx. It truly is a vector, but it's not a vector in the real world. It's a vector in this other abstract space that we're not really worrying too much about. But it is a full vector space, and we like to think about it like that. If we want to ascribe it meaning, now it's a little bit facetious to ascribe it meaning, but if we want to ascribe it meaning in regular space, regular real life space, because I know a lot of people do like to ascribe it meaning, to ascribe it somewhat false meaning, but it's good for intuition. Somewhat false meaning in regular space. We can. And in that space, it describes an infinitesimal change, specifically in the x direction, right? Because my higher dimensional spaces have multiple directions I can walk in. The dx, if I want to ascribe it some sort of regular space idea, has an infinitesimal change specifically in the x direction. But in some ways, we shouldn't ascribe it that meaning, right? We should try to think about it as truly this element in the cotangent space and nothing more. But a lot of times, people like to think about it as that infinitesimal in the x direction of regular space. So now, how can we interpret the derivative? What does it mean to put dx in a denominator? If dx is a vector, right? We just kind of decided that dx was a vector. How do you divide by a vector? You don't. The notation ddx isn't so great. What you can do, though, is you can project onto the direction of a vector, and especially because it's already a unit vector. So dx is already a unit vector. And we can project onto this direction. And that's really what ddx means. It means you're going to project onto the direction dx from what other vector? Well, we know that the total derivative is, well, it's really a matrix, but all matrices exist as vectors inside of their own vector space. So you project the matrix, right? This is the matrix or vector, whatever you want to think about it, in the cotangent space. You project specifically onto the direction of dx. That's what this true d dx is referring to, and now you've found out why they didn't tell you that in Calculus 1. It's really not an easy thing to wrap your head around in Calculus 1. Everybody would get more confused. You basically need linear algebra to have any sort of idea of what's happening with projections. So it's not really a fair definition to make in Calculus 1. But this is really the definition we should start thinking of. And it allows us to say, hey, wait a minute, partial x is actually the projection in the dx direction. Partial y is the projection in the dy direction. And partial z is the projection in the dz direction. We're really taking projections of the total derivative every time we take partial derivatives. So I've got the following plot here to give us an idea. We still have, so we've got df here. This is a vector in the cotangent space. Once again, don't really worry about what that word cotangent means. It's just irregular. It's not the space we like to normally think about, but we should think about it here. df is a vector in that space, and that vector includes an x component, y component, and z component. And of course, you realize those components are they're the entries in the total derivative, or equivalently, they're the partial derivatives, right? So it includes these three components. And then what I have here is I have the components that are projected downwards. That's partial f, partial x. This is partial f, partial y, and this is partial f, partial z, because I've actually performed here. I've projected down to the xy plane and then over to just the x direction. Here I've projected over to the zy plane and then over again to the z direction. And then here I can project down to the xy plane and over to the y direction, right? So projecting that vector onto each of the axes, really decomposing it into each of its fundamental components, the x, y, and z components, those are the partial derivatives. We can, however, ascribe even these objects, right? We can still do the same ascription and ascribe df, the total derivative of my function f, we're going to ascribe it an infinitesimal shift of a point in regular space. Okay, so df is some infinitesimal shift in regular space. And in fact, whose directions precisely correspond to each of, well, the projections, right? The projections, but we know the projections are partial x, partial y, and partial z. And so you see I've included infinitesimal shifts of partial x, partial y, and partial z away from some point in regular space. That's really what's going on with differentials. And that kind of describes what's going on with differentials in a derivative setting. What the heck happens in an integration setting? Because in Calculus 1, we also use this differential dx to describe an integral. And now that we know it's a vector, this is starting to make a lot less sense. Why and or how could an integral be multiplied by a vector? Right, there's this dx multiplying everything else in the integral. What does it mean to take this function here? This function is just a scalar field, some collection of numbers. You're going to multiply it by a vector, and then the integral sign just means sum, right? It's an infinite summation. That's why it kind of looks like an S, right? Summation. So it's this infinite sum of a bunch of numbers that are multiplying a vector. How do we interpret that? Well, it makes a little bit more sense to interpret it over a definite domain. So let's give ourselves a lower bound and an upper bound that we're actually going to integrate over, and then I'll describe how this makes sense to think about as a vector. Well, I'll say in words first. We think about this integral starting at x min and ending at x max of f of x dx as infinitely many, infinitely small vectors. That's the dx term. These are the dx terms, so we have infinitely small vectors here. Each are in the direction of x, right? Because those vectors point in the direction of x, and they're infinitely small vectors in x. However, I'm multiplying every single one of those vectors by f of x. In other words, I'm scaling a vector by the value of f of x. I'm scaling every single vector by f of x, and then I'm just going to add all of those vectors together, right? We can add vectors together, no problem. What does this look like? Here I've provided a plot, which I'm planning on integrating for everyone. We've got a function up here, f of x, and then what I've described, I shaded the area. Everybody knows that the area of the integral, in this case, looks like 0 to 10 of f of x. This is just the shaded area. But that's not really how we should think about this integral. We should think about the integral as, well, f of x has some height here, height, all the way around. There's all of these numbers that correspond to a height. But really, we're going to think about that height as just a scaling coefficient for dx. And we all know from what we learned, dx is a vector. It's an infinitely small vector in regular space. So we have this scaling coefficient for an infinitely small vector at every point in time. What am I trying to describe at the bottom here? Well, here I'm close to 0. Here the value of my function is close to 0. I'm not scaling my infinitely small vector by very much. But as my function moves up here, maybe my function over here, I start to scale that vector x by a little bit more. I start to scale it by the size of f. And then f gets pretty large here, and you start to scale really by quite a bit, right in the middle there. And then it starts to fall again, right? The values of f start to fall. So I'm scaling that vector less and less as my function gets closer to 0 here, and less, we end up getting close to 0 right there, right around 10. It's probably a good idea to say this is about 10, the area of that first piece. But then it happens again, right? My function, even though it got down to 0, now it starts increasing. And as my function increases, it starts scaling dx more and more. We get bigger and bigger scalings of dx that we're continually adding together. We end up at the top here, and we've scaled, right? These later vectors are scaled by a lot larger values. We've placed them all end to end, and we have kind of this total value of the integral that's about, right? Total integral value is about 27, just by adding a lot of scaled vectors together. That feels weird, right? It feels weird. We think about integrals as areas, but in true differential senses, with a dx, the integrals are not areas. They're describing total lengths, right? This is really a total length of vectors lying end to end of the form, right? They're end to end. Each one is scaled by f of x. Each vector is scaled by f of x. And technically, there are infinitely many, infinitely small vectors. So I know it's a little bit abstract, a little bit confusing. We still haven't quite learned what those wedges are for yet. We just learned that they exist and how to think about dx as a vector. Let's move on to this next section so that we can get an idea of what those wedges are actually doing. So we're going to talk about the exterior wedge product, and I'll say the exterior derivative for the next video. Starting with this wedge product, this is the wedge that we saw at the beginning of class, right? Wedge, 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 wedge. And we also are aware now that dx is a vector, dy is a vector, dy is a vector, dz is a vector. And of course, each of those still vectors. So in other words, wedges, what do wedges do? They combine vectors together. How are they going to combine vectors together? They're going to do it in a product sense. What do I mean by a product sense? Let's just think about some numbers here. Let's say I'm going to multiply 9 times -3 symbolically. I'm not actually going to say this is equal to 27 at all. I'm now going to ask questions. What are natural properties of multiplication? Well, one of the natural properties of multiplication is if I turn around and I multiply 9 times -3 by 2, I can represent this either as 2 times 9 times -3, or I can represent it as 9 times 2 times -3. In other words, if I multiply by a new number, I can pass that number to the left term, to the 9, or I can pass it to the right term, to the -3. Shouldn't matter. Another nice property of multiplication is if I turn around and I decide to add 9 times 5 to my original 9 times -3, I can factor out a 9. And 9, because the 9 agrees in both terms. That's what's important. Is the same number needs to be there, but as long as the same number is there, I can factor it out. And I can just write that as 9 times -3 plus 5. So you have this idea of distribution, or really factoring, which is the opposite of distribution. And normally those are the only two requirements to call something a multiplication or a product in most mathematical settings. But of course, something that you could say is that this should be equal to 3 times 9. That's normal, at least with the multiplication we know and love. Unfortunately, this property is not universal for multiplications. Why do I say that? Well, you've already experienced matrix multiplication where you saw that this isn't a true property. And so we're actually not going to require it for our wedge product multiplication either. But those first two should still be true. So how does the wedge product get defined? It's a multiplication on vectors is what I said, right? So let's give ourselves 2 vectors, and let's say we've added those vectors together, and then they have a wedge product with a third vector, z. Well, this is just like the case you saw. Let's say I have a 9 times -3 plus 5. You would want that 9 to be able to distribute to 5 and distribute to -3. So you want your answer to be something like -3 times 9 plus 5 times 9. So we want the same thing from these vectors. If we take a wedge with z, we want to be able to distribute that wedge with z to both the x and the y. So we can say it's x wedge z. That's the same as -3 times 9 plus the plus survives, and you say something like y wedge z. That's the same as the 5 times the 9. So this idea of distribution, you can distribute products, right, over addition. And this is what we want out of the wedge product. We can distribute in the other direction too, right? 9 times -3 plus 5 is going to be 9 times -3 plus 9 times 5. And then similarly, we want multiplying by a number, c. This would be like 9 times 3 times 5. We want this to be 9 times 3 times 5, or equivalently we want it to be 3 times 9 times 5, right? This multiplication by a different number, by a scaling number, should be able to pass to either of the two terms on the inside. And it does not pass to both. That's what's very important here. It passes to either, but not both. Now, the special thing about the wedge, this is the only kind of funky thing about the wedge that gives it all of its unique characteristics, is that if I exchange the order of any wedge, so I start with an x wedge y, let's say I want to exchange the order to y wedge x, I have to pay the price of a minus sign. So that's what's going to be special here. This is called, there's a word, mathematical word for this, it's called an alternating product. Because, of course, if you exchange the order, the sign alternates between -1 and 1. It's actually a consequence of the third property, that when you flip the order, you get a negative, along with the first property, that you can combine some terms over addition, and then eventually with the middle property, pulling a 0 out, you find out that a wedge product of a vector with itself is always 0. So if you take an exterior product of any vector with itself, I necessarily recover 0. And now you start to see why we've prohibited these vectors, right, in differential form, something like dx wedge dx in a differential form. It's because it would have been 0 anyway, according to our rules of the wedge product. Now, I say, unfortunately, well-defining an object doesn't do much to help one understand what it is. The next remark is going to help us resolve what it actually is. This remark is awesome. This remark is everything you should take away from today, aside from the fact that the differential is a vector. This remark says, the exterior product, or the wedge product, establishes vector spaces of lengths, areas, volumes, and hypervolumes. In other words, we always ascribe vectors as having a length. So just be like my vector x has some sort of length, right? Vectors represent lengths. But then if I decide to take x, wedge y, this vector I'm going to allow to represent an area. And if I take a vector x, wedge y, wedge z, I'm going to let this vector represent a volume. If I have something like x, wedge y, wedge z, wedge w, I'm going to interpret that vector as representing a hypervolume. Now it's weird to say that like all vectors have magnitudes, right? So that one makes a lot of sense, that the magnitude of that vector is its length. This one's going to make a little less sense. You can compute the magnitude of this vector, and you'll get a single number out as the magnitude, but really the meaning you should ascribe the magnitude of that vector, it represents an area. This goes back to like the cross product. You would take a cross product of two vectors, and you would get a third vector, which if you computed the magnitude of that vector, didn't represent the length of, I mean, it did represent the length of the cross product vector, but it also represented the area of the parallelogram spanned by those two vectors. So that's really what we're thinking here, is that these vectors, their magnitudes are really corresponding to some higher dimensional quantities. Now, why should those quantities be considered vectors? It's actually not too hard to argue why. Let's recall what vectors have to be mathematically. Anything that's a mathematical vector is just an object that can be added to another object, added to another vector, and scaled by real or complex numbers. So as long as areas can be added together, which we do all the time, add integrals together, get areas, add areas together, or scaled by real numbers, you can pass scalars in and out of integrals. So areas can be added together, they can be scaled. That makes them vectors. It feels weird to think about them as vectors, but it does make them vectors. Same with volumes and so on. I've got some nice graphics to help us think about why areas should be able to be vectors. Look, we've got a square here. I'm going to add it to another square here. And I have now a vector that's twice the length of the original square. So there's the vector that's kind of representing the two squares together, added together. The magnitude of this vector corresponds to the area of both squares. Similarly, I could take squares that are pointing in opposite directions and ascribe them a negative area, right? If I want to assign both positive and negative areas to objects, I can just say that my squares are pointing in the opposite direction, and I'll give them negative areas. And then my vector here, right, goes to the -2 direction instead of the +2 direction. Or I could have with my one square, it's a square of area 3, and then my second square, a square of area 1.5, and then we look at our vector and add them together, and we have a vector of length 4.5 there, just like you would expect areas to add. Or in fact, in this latter case, I still want to emphasize that there was a full rectangle of area 3 here. I've just used a negative 1.5 area rectangle for my second one, so they no longer add together, they subtract, and what I'm left with is just a vector of length 1.5. So I'm just trying to emphasize that areas certainly can be considered vectors here. I would suggest you just read this part rather than actually watch me talk about it, because I don't think talking about it is that clarifying. Here I've got the same cases with cubes, right? So we can certainly add two cubes. There's a cube of volume 1, and then here's a cube of volume 1, and if I add those cubes together, you get a vector of length 2, or I could think about cubes with negative volumes, right? Here's a cube of volume -1, here's a cube of volume -1. If I add two cubes of volume -1 together, I can ascribe it the vector which has length -2, or at least it's pointing in the -2 direction. Right, so you can add volumes together, you can add areas together, you can also scale volumes and areas as much as you want. Nothing too special, but now we think about the exterior product as being the vector which describes areas. And so what I have here is I have the vector 1, 2 wedge product, the vector 2, 1, and we think about here's the vector 1, 2 drawn, here's the vector 2, 1 drawn, and here is the area spanned by those two vectors. It's the parallelogram created by pulling the two vectors across from one another. And so this parallelogram has an area. The area would be whatever this vector, the magnitude of that vector actually is. So area of parallelogram is the magnitude of 1, 2, wedge 2, 1. Now it's a magnitude within the vector space that we actually embed this. We haven't really defined that vector space. In fact, we don't use it too much, but it's good to know that this area exists as the magnitude of this vector. But in some ways, the vector itself, it doesn't even need a magnitude. It just represents the area. Represents the area, I should say, it represents this shape as a whole. Right, the wedge product just represents the shape. Is all it means. It's just a shape, a parallelogram shape. And you can do the same thing with 3-dimensional vectors in 3 dimensions. I've wedged 3 of them together to give me this parallelepiped, which looks like the following, 3-dimensional structure I have here. This wedge product just represents the entire 3-dimensional shape. And then, of course, its area corresponds to the magnitude of that vector. And so now we have vector spaces of higher dimensional spaces. That's what the wedge product can do for us. And we can start to answer, what are these differential forms talking about? Well, we know that this in regular space, quote unquote regular space, is the infinitesimal in the x direction. And dy in regular space is the infinitesimal in the y direction. And so we can think about, here's my dx vector, here's my dy vector, and when I wedge them, I'm thinking about this square. It's literally the square, and if I go ahead and think about them as infinitesimals, then this is a square of infinitesimal size. Square, comma, in the xy plane of infinitesimal size. That's exactly what these wedge products for differential forms are doing for us. They're allowing us to construct squares, parallelograms, even cubes, right? Cuboids or cubes here. What we have with dx wedge dy wedge dz, that's going to be, well, here's the dx infinitesimal, here's the dy infinitesimal, here's the dz infinitesimal, and now that gives me this little cube of infinitesimal size that I can then start using inside of an integral and add a lot of cubes together. Add a lot of cubes together. So here's another example of that. We think about dx and dy as this square embedded in two-dimensional space, but you could think about it as the square embedded in three-dimensional space as well, dx wedge dy, and then something like dy wedge dz is going to be the square embedded in three-dimensional space but lying within the xy plane. And you can think about dx dy dz as the cube in three-dimensional space that moves outward by 1 unit in each direction. So I've got this last remark, and then we're going to finish up for the day. You can actually consider the exterior of the wedge product really as the vector space of determinants. It should have started to feel familiar if we were talking about areas of parallelograms, that this really is the determinant. We kind of are doing determinants here. So what we want to think is that if we have a determinant of a 2x2 matrix, and you add that to a determinant of a 2x2 matrix, and in particular, these first left entries are the same, x1, y1, well, those determinants end up adding together just like you would expect. You can just add the second terms together, x2 plus x3, y2 plus y3, and then just compute the determinant of that following matrix. This does behave exactly like, this would be the situation of x wedge y plus x wedge z equals x wedge y plus z, right? It kind of does the same thing. We can think about determinants with scalar multiples the same way. If I multiply a determinant by a number, you can just pass that number into only one of the columns of the determinant, right? You can't pass it to every single column in the matrix, but only the left column or the right column. This would be like c times x wedge y is equal to c times x wedge y, right? The other property of our wedge products. And also, you've probably seen before, if you took a linear algebra course, that if you swap rows or columns around in determinants, you pick up negative signs. And picking up those negative signs is exactly the same negative sign that you pick up when you swap around x wedge y. So these really are, these wedge product exterior products really are like the vector space of determinants. We just kind of notate them in a different way. And they do give us a little bit more ability than just determinants. So what's really cool is that this idea of interpreting the wedge product as a space of determinants gives us a new way of thinking about the cross product and really understanding where it came from. Because we'll recall the cross product of two vectors, x1, y1, z1, and x2, y2, z2, as well. For the first entry, you cross out the x direction, and you do the cross product y1, z2 minus z1, y2. And then you cross out the middle column, you do z1, x2 minus x1, z2. And then you cross out the bottom column, you do x1, y2 minus y1, x2. As a cross product, you could ask where that came from, because you'll recall that the magnitude of the cross product computes the signed area of the parallelogram spanned by the two argument vectors. So that really is the wedge product of these two vectors. They should be one and the same thing. And then we also know now that our wedge product can be thought of as determinants, right? Determinants of matrices. But then the big question becomes with this cross product, well, we only have two vectors here. You can't really take the determinant of a matrix which has two three-dimensional columns, make it not square. You can't take the determinant of a non-square matrix. So what we do is we actually include different unit vector directions. This is the x direction, the y direction, and the z direction as the three entries in our last matrix, because actually, right, that's the x, the y, and the z directions of our outputs. And then at this point, if we compute the determinant of these two columns brought right next to each other along with my x, y, and z directions, we are actually computing the wedge product here of the two entries. And when you compute that determinant, you get exactly the cross product coming out, as long as you interpret each of ux, uy, and uz just as saying, hey, this is the x component of my cross product, this is the y component of my cross product, this is the z component of my cross product. So it's kind of cool that this gives you another way of coming up with the cross product. Anyway, I know it's been a really, really long day. It's also just cool stuff, though. I hope you really think it's cool. I really think it's cool. We're going to talk about the exterior derivative. Basically, how do we compute derivatives of differential forms in the next video. See you then. Bye.